Well, welcome everybody. Thank you for coming. This is the parallel session of the Milky Way and its components. And well, first of all, to say thank you to all the people that sent their contributions. And basically in this session, we will do a first short summary of all the contributions you sent. We need to apologize because we have very short time. So we will try to do our best to summarize well all the contributions and to mention everybody that sent a contribution. But all the contributions are extremely interesting, but we have enough time to devote specifically to each one of the topics that you sent. And we basically will present this summary myself, Sergio Simon Diaz, you can see him also here, and also Eva Villaver. We are the three coordinators of this session. And well, after these 20 minutes of short summary, we will have 25 minutes of open discussion in where you will be able to ask any question you have in your mind regarding the contributions we will summarize. So I will start, I will be the first one with the first part of this Milky Way and its components parallel session. Let me share my screen. That is this one. Okay, as I told you, we have 82 contributions. The first, we divided all these contributions in a smaller subtopics, subclasses, and the first one is the Milky Way formation and evolution. In this subclass, we had 5 contributions. The first one is from Gallard and collaborators. Basically, what they did it was to use CMD and inner halo stars, and when comparing it with cosmological simulations, they finally discovered that 2 different paths in the CMD plots are due to the formation of stars in the Gaia Enceladus, and on the other hand, also in the inner halo of the own Milky Way. So these are the 2 components that generated these 2 paths in the CMDs. Also using CMD fitting, we have another contribution from Ruiz Lara that what they did, it was to do this CMD fitting to obtain the star formation history of the Milky Way at around 2 kiloparsecs around the sun, and they found several star formation peaks in the past that coincide more or less with the Sagittarius galaxy. Related with this, we also have the contribution from Moore and collaborators, where they also using Gaia DR2 data and based on some galaxy model, they obtained also that there was a star formation peak at around 5 giga years from now, in where some part of the Milky Way was formed. Related with the star formation history of the Milky Way, we have the Roca Fabregat collaborators' work, in where they found that basically these star formation peaks, these star formation events in the Milky Way, had an imprint on the chemistry of the thin disk, and in this case, in the lithium distribution of the thin disk. Finally, also in the Milky Formation and Evolution section, we have a work by Sotillo Ramos, in where they use the TNG15 simulations to try to understand how different accretion histories generate or not similar galaxies like the Milky Way, all the components observed with the Milky Way. In the second subsection, that is the chemistry of the Milky Way, we have 3 contributions. The first one by Arellano Cordova basically uses H2 regions and obtains the metal from spectroscopy. And they also use the parallaxes from Gaia DR2 to study the radial abundancy gradients. And they discovered, among other things, they discovered basically that something that it was proposed in the past, there was a flattening of the oxygen abundance in the central regions of the galaxy. It doesn't exist, in fact, in the data they analyze. And by present further results from analyzing old open clusters inside the Ocaso survey. And basically what they want is to get a better determination of the chemical abundances and radial velocities. Finally, also in this section, Vizcasillas Vázquez, they analyze the neutron capture elements in different regions, in different structures of the galaxy, and they propose that these elements can be used as cosmic clocks to study the galaxy formation history. Another subsection, the kinematics. I have here 4 contributions. The first one by Anders and collaborators studied the stellar radial migration in the disk of the galaxy, and they discovered basically that it cannot be modeled like a diffuse process, but modeled like a sub-diffuse process. That is something that is not being done until now in research. A second work is by Anguiano, and what they did basically was to study the velocity distribution function of the different galactic components using Gaia data and apogee chemistry. The contribution by Miret Roche, they basically study using Gaia DR2 data and radial velocities from ground-based facilities. The beta Pictoris moving group, and they obtained the traceback age that fits very well with the isochronal ages and also with the lithium depletion boundaries. That is the first time that these estimations of age coincide for a moving group. Finally, Garcia Conde and collaborators studied using a cosmological simulation called Garrocha that the phase space covered in Gaia in the ZZ space can also be seen in cosmological simulations, and they study how these phase space spirals can be produced. And going to the last 2 subsections of this part, the stellar structures in the disk, Anders and collaborators reanalyzed the last populations using Gaia DR2. They compared with the old catalogs, and they basically discovered that the old catalogs were incomplete and impure. The cluster stellar age function needs to be revisited. Zhrobakov and collaborators analyzed it also from Gaia DR2, analyzed the density maps in the Milky Way to study the warp, and they found a clear age dependence on the amplitude of the warp. Also related with the warp, Pardo Araujo used test particles models inside Milky Way like galactic potential to see if a precessing bar can be the one that provokes the formation of the warp. Unrelated with the bars, Romero Gomez and collaborators basically used Gaia astrometric observables instead of parallaxes to plus Gaia mock simulations to try to constrain the bar pattern speed and also the bar orientation, something that is still completely unknown. And finally, the structures in the halo and the outer disk, with work by Antoja and collaborators, that they basically found a very big sample of stars in the Sagittarius dwarf and also in its stream, basically 360 degrees in the full sky, and also they found RR Lyrae inside of them, so they could also determine the distances. This can be also used in the future to constrain the potential of the Milky Way. Miro Carretero also traced is doing a work tracing the tidal streams in the in this case, they propose a new photometric method based on narrow and intermediate band filters to determine the metallicity of these halo metal core stars. And finally, Ramos and collaborators, also using Gaia DR2 data, studies the outskirts of the Milky Way disk. They apply a wavelet transform to try to better define the density structures in the data, and they found that there are these structures in the outskirts of Milky Way, for example, the monoceros ring and the anticenter stream, that they think and they try to demonstrate that are basically originated by the disk, not streams in the halo. And this is all from this first part of the structure. And I have here some questions that maybe you can be interested in comment in the last part of this Milky Way and its component session. If you want, you can write down your comments for this question and then raise hand at the end of the summary. And thank you. And now I give the word to Sergio Simon for the next part of the summary.
Okay, thank you very much, Santi. Now I'm going to share my screen here. We go here. So this is the second part, and I'm not going to give many details on each of the work because this will be crazy. So basically what I've done is similar to Santi, I've divided in big blocks, so you can better identify the posters you are interested. And then I'm going to start with the one I feel more comfortable, that is massive star, that is my domain of expertise. And I was very surprised, I found it very interesting that there were already 1, 2, 3, 4, 5 talks or contribution related to binaries along massive star evolution. This is one of the hot topics nowadays for the massive star community. So it's very nice to see that people working here in Spain goes from the study of binaries in the O-star domain, like trigueros. Also, in the case of Blavatsky, concentrated in the fast rotating O-type stars that are kind of has some implication for the evolution of massive stars. Then in my case, I concentrate on the B supergiants. And finally, Patrick had 2 different contributions about the red supergiants. So basically, we are covering all the different evolutionary stages. And one important message, apart from the percentage of binaries here, is that we have to also take care of spectroscopic variability to really identify properly the binaries. There are another 2 very interesting contributions by Silvia Martinez and Mata Sanchez about 2 binary systems, very special binary system. One is eclipsing high mass X-ray binary with a B supergiant, and the other one is a millisecond pulsar plus an extremely light helium core white dwarf companion. I think they put very interesting empirical constraint to both the properties of the winds of massive stars or the binary evolution models. So you can have a look in these contributions. Then in this second block, I put together all the contributions that are kind of providing useful things for future investigation, is to that they also provide some example of what can be done with them. And basically we have, in the case of Garcia Vargas and myself, we are providing new spectroscopic, high quality spectroscopic data with JTC, Megara, and also with Hermes and FIES. Then we have several kind of more photometric surveys. One is with GTC, OSIRIS, that is the broadband data archive that they also use for the discovery and identification of asteroids and cool dwarfs. And then we finally have here this IGAPS catalog that is combining the IFAS catalog and the UVEX survey of the whole northern galactic plane by Maria Monguió. And then we have another 2 that are using telescopes there in Javalambre. One is by Lopez San Juan, who describe a bit the J+ survey and apply and use it for the study of white dwarfs. And then we have Galante, presented by Gonzalo Holgado, that is a photometric survey to identify OB and world bright stars in the galactic plane. So I'm sure we will have many possibilities to do good science with all these incredible data. And then we are also getting ready for future surveys. One of them is the case of Artemio Herrero, who described what is called the WIF Cygnus High Resolution Survey. Is one of the surveys that will be done with WIF, starting hopefully by the beginning of next year, if everything goes as expected. And also there's a very interesting contribution by Eduardo Martin about using the Alhambra and Cosmos survey in preparation for the Euclid legacy science that will be done in the case of ultra-cool dwarfs. So they detected more than 800 ultra-cool dwarfs. And this is kind of some preparatory work for the future. Then talking about tools, we have also many different contributions presenting either codes for the quantitative spectroscopic analysis of different type of stars, as in the case of Tabernero and La Varga. They are basically obtaining parameters of AGKM stars and also being able to characterize or extract information about the chromospheric activity. Then we have the Young Star Pipeline by Alonso Santiago and Frasca. and 2 services that are offered by or 3 of them, because Clusterix is also there in the virtual observatory by Rodrigo Blanco, 2 of them who provide both filter profile service that is very useful for many aspects of our investigation, and also what they call BOSA 7, that is a tool to analyze the set of different objects. And then we have this very interesting tool developed by Lola Balaguer. Clusterix is basically to use information from proper motion, parallaxes, and other information to identify clusters among images with the stars. Then we have this nice summary presented by Cheska about where we are and where we go in terms of Gaia. And she also summarized what has been done by the REC. And I found it very interesting in this figure how things are going to improve in year 3. So looking forward to see what we can do with this new data. And then I put in this block different examples of works of studies using already data from Gaia year 2. So one of them is by Carrera. He studied in detail one open cluster, one of the nearest old open cluster, M67, and found very interesting conclusion about what is the spatial distribution and the dynamical evolution. Then we have 2 different studies, one by Berlanas and the other one by de Burgos, who consider 2 different OB association. One is Cygnus OB2, that is at the center of the Cygnus X region. They both use Gaia plus some ground-based spectroscopy to characterize the massive star population and also identify runaways and binaries and other things that are of interest for the study of massive stars. Then Pérez Blanco investigates also with Gaia the clustering properties of Herbig AEPE stars using also the serial code. And finally here, Castro Guinard used Gaia tier 2 and their own tools to identify the galactic open cluster population. And it's very interesting. I think this catalog is going to be very, very useful because they detected 650 open cluster, and some of them are detected at distances that were thought to be kind of complete, but still we are discovering interesting things using Gaia. And finally, this is the last block in which I put all those contributions talking about molecular clouds or star formation processes. So some of them, like in the case of Areal, Rodriguez Vara, and then Palau Puigvert, they basically go directly to the study of the molecular clouds with different techniques, and basically provide empirical information for our understanding of the evolution of these molecular clouds and how they connect with the star formation processes. And then we have the last 2 are more related to star formation processes. It's the case of Mignon Cris and Marcos Arenal. Basically, one of them is studying the accretion during massive star formation. And then we have connected to the formation mechanism of planetary disk, a study of a disk around Herbig P stars. I think, yeah, this is basically all I wanted to present in this part. And before passing the torch to Eva for the last part of our summary, I put also here some questions. Maybe you can have a quick look to them. These are just in case there are not interesting things proposed by you to discuss, but hopefully there will be many, many interesting things here from your side. And I'm going to stop sharing, and you can go ahead whenever you want, Eva.
Hello, everybody. You have me? Hello? Yeah?
Yep.
Is it right? Okay. So I'm sharing the screen? Yeah, right?
Not yet.
Not yet.
Okay.
Ahora sí.
Here we are. Hello, everybody. If you haven't heard about your contribution yet from the talks of the previous two talks, it's my turn. And obviously, I have a mix of many things as we have to fit many different parts of science in this section. Let me first start with binaries. Sergio already mentioned binaries in massive stars. Here we are dealing with binaries in low mass stars, in the central stars of planetary nebula. And before going into the science, I would like to remember somebody that worked in this area and that we have lost recently, Rebecca. We not only lost a fantastic human being, but we will miss the contributions that she will make to this part of the science. So I wanted to start by remembering her. And going now to the science of the people that we have around, the fantastic science that they are making. Let me start with the contribution of Ayer, that in which they are using tests to search for binary central stars of planetary nebula. I mean, the search of binaries among this type of stars is important because now we are realizing that probably the morphology of these systems is defined by the binarity of the central stars. But not only the binarity influences the morphology of these beautiful planetary nebulas, as we see here in the helix, where they have detected variability. I yet have detected it. But they also influence the evolution of the star. And we have systems like the post-red giant branch stars that get their evolution truncated because the presence of a component there probably makes that most of the stellar evolution is truncated. Then we have people that are looking for binaries with using Gaia, which is one wonderful thing to do with these stars, because as we have the problem many other stars, we have a problem with the distances. So here González Santamaría look for binary stars in the touch systems in planetary nebula with Gaia. And finally, in this part, we have the contribution of Mundai, which defined the post-common envelope evolution, something that has gone through interaction in the binary evolution of a star in a planetary nebula that is very interesting because the primary is very massive and might make it into supernova 1A. So this is stay tuned because this is very, very promising. And then I will move into the determination of fundamental stellar parameters using different tools, methods, and a mix of a little bit of everything. Here we have in the top the contribution of Kruth, in which they look for the radius anomaly in short period eclipsing binaries. Basically, they find that the secondary stars are inflated, and they are more inflated if they look into the low mass star, which is very important because we need the mass radius relation for these stars, and if they are very close and they are inflated, we have something to understand there. We have different people using different techniques in order to understand the evolution of the stars and determine the fundamental parameters. For example, Mazur studies surface rotation and magnetic activity of thousands of stars with Kepler, and define, I mean, it's a way of trying to understand something basic, which is, for example, how magnetic braking operates, and they are finding some stalling on the magnetic braking, which is important for studies of rotation with age. We have also tests playing an important role for the determination of fundamental parameters of delta Scuti stars from Barceló, Fortaleza. And we have tests again for asteroseismology of solar-like stars. Here I put a contribution as well of Jones, in which they provide the community with a code for binary star modeling. And I put it here in this fundamental stellar parameters because with the modeling of this free code, they are providing tools for determining these parameters. We have more contributions using surveys. In particular, Gaia is playing a key role in this part of the science. For example, we have people trying to establish the age of clusters using the equivalent width of the lithium line in different clusters, more than 20. We have people looking, like Jimenez Esteban, that they are studying the volume limited sample of white dwarfs using Gaia and VO tools. Also a very important tool that we cannot forget to mention, the virtual observatory. We have people using machine learning and Gaia, like Bioke, to catalog high mass priming sequence and classical big stars. And we have classifications of L and T dwarfs using a combination of different surveys and trying to determine the scale heights of the different components of these low mass objects. We have, I put all the contributions by Cármenes because although they are not all the same at all, they all fit this, I think, fundamental parameter space in which big surveys led by researchers from the land, let's put it this way, using a fantastic instrument and a combination of science and tools and hard work. They are putting a lot of catalogs in the study of M stars, but not only M stars, but FGK and so on. And they are studying basically everything from the kinematics, moving groups, and trying to determine where they belong or not to these different kinematical components, like Cortes Contreras, to the determination of stellar morpheric parameters, comparing different methods and tools, chromospheric activities by La Varga, for example, or the work by Montes that identify as activity indexes in the Cármenes spectra and the catalogs that they have available. I think we are going to see a lot of publications from this. I mean, we have already seen a lot of them, and we will see more because they have an important and very valuable database and unique that they will keep extracting information. If we look at the chemistry, we have very interesting things, like, for example, the discovery of phosphorus-rich stars by Maceron. We have the study of stars enriched in neutron capture elements. We have the study of Garcia Rojas, where they use planetary nebula with MUSE. I mean, something that is very interesting in order to study the difference in the ionization correction factors, in the discrepancy between the abundance determinations that one can get from recombination lines from the collisional excited lines. And we have also the study of Méndez Delgado, where they study the photoionization of Herbig-Haro objects and the chemistry in the Orion Nebula using VLT. Also, the contribution by González Hernández, I find it very unique as well, because they go for the very iron poor dwarfs, and they study the enhancement that they find in elements of the CN, carbon, nitrogen, oxygen cycle. This is important because it gives us clues of the chemical enrichment, not only of the local, but we can go very far past for the chemical evolution of stars in the galaxy. Now we have a mix of things. We have disks, low mass substellar objects, planets, and even studies of habitability using cosmic rays. Here, I think there are very interesting results by, for example, Rivas, where they combine artificial neural networks to the study of planetary disk. They combine it with models, and they revisit what we already know on what we knew on these systems. Or, for example, the proposal of Clement, where they use interferometers to not only to study the multiplicity of very low mass objects, but also they propose to study interferometrically the interaction between a planetary magnetosphere and the star, which is something that hopefully in the future we will see happening. Finally, we have the studies of Herbie disk here of, for example, Mendigutia, from which I took this picture, in which they try to understand how stars grow when they are young. And basically there are two mechanisms: magnetic accretion, like the one in the top, and then we have accretion through the boundary layer. And in between, we don't know basically what happens. Maybe it's a mix, and this is apparently what they are starting to be arguing and finding. And that the early A stars accrete more through the magnetic channel, but as we go into the B, it's not so clear. And also we have studies of disks by Gregorio Monsalvo, where they study at centimeter wavelengths the transitional disks surrounding T Camaleonis, and we have these beautiful images here. And that's it. I think now we should move into the discussion. And we give the word to everybody that raised their hand. Try not to speak all at the same time, because we will close your mic. And basically we leave a free discussion. We will keep all the topics open, and but we try to channel them through all the 80 contributions that we have had in this section. So, who wants to be the first one?
There's a question in the chat for Lola Balaguer Núñez. Please, Juan, you can turn on your micro and you can make the question to Lola.
Hola, buenos días, buenas tardes. Mi pregunta es sobre Clusterix. En la presentación se habla de su aplicación para discriminar estrellas de campo con respecto a cúmulos abiertos. Y mi pregunta es si se podría utilizar Clusterix también para discriminar estrellas de campo frente a cúmulos globulares. Y cómo se haría eso, cómo se podría aliviar el problema del overcrowding en el centro. Gracias.
Claro, la herramienta está pensada para usar movimientos propios. Entonces el problema del overcrowding lo tienes para los movimientos propios. Si no tienes buenos movimientos propios, es difícil. De todas maneras, en el caso de cúmulos globulares, diría que sus movimientos son muy diferentes a los del campo, con lo cual si tienes movimientos propios no te hace falta tampoco una herramienta demasiado sofisticada para separarlo directamente a mano. El problema lo tienes para el cálculo de los movimientos propios en zonas de muy overcrowded.
Okay, gracias.
A ti.
We have more questions? Yes, please use English if you can.
I see we have a comment by Sebastián Barceló. If you want, Sebastián, you can turn phone.
I didn't understood you. I have some problem with the sound.
Haz la pregunta tú, Sebastián.
No, era solo una puntualización. Que nosotros no hemos estudiado estrellas con pulsaciones de tipo solar, sino estrellas delta Scuti. Y para las... nuestra intención era encontrar un índice sísmico, algo en las pulsaciones, un parámetro que nos pudiera indicar cuál es su temperatura. Simplemente.
He dicho tipo solar, perdona.
No, más que era en la presentación estaba puesto Solar Light Pulsators, era por si acaso alguien leía y... Muchas gracias y perdón.
We will make the presentations available later on, so we can correct this. Please, if you find typos or whatever in one of the presentations, let us know and we will correct that. There is a question by Jose Caballero to the Gaia team. What is the current data release schedule? What is the status of determining parallaxes of very bright stars? And if you can answer in English, it would be good. Thank you.
Hi, this is Karma. I can say that the releases, the schedule of the releases are explained in the Gaia page. Currently, the data release tree will be split into two parts that I guess everybody is aware. The first part will be released at the end of the year. It will contain astrometry, means positions, proper motions and parallaxes, plus photometry. This means the G band and the integrated BPNRP. And we will also include in the catalog the radial velocities determined in DR2. So the sources will have complete kinematics and photometry. And then there will be the full data release tree that will include as well the new radial velocities from DR3, astrophysical parameters, multiplicity and some classification of extended objects and so on. And this will probably go at the end of 21st, the end of next year. And then about the parallaxes of very bright stars, so the improvement in the parallaxes and proper motions roughly corresponds to a factor that is because of the extended period. We cover now 34 months of mission, so it means that we have more observations, and this automatically implies a better precision in proper motions and parallaxes. But as well, we have our calibrations have improved quite a lot, especially in the bright part. And in the bright part, we have improved the releases more than in the faint part. And I think that in the poster by Francesca and us on the Red Española of Gaia, we have included some plots. So there you can look at the plots and see which the mean values of the uncertainties. I think it's there.
Thank you, Karma. And now I see that there is a question by Sergio, I think, to Castro Guinard.
Yeah, I have a question myself to Castro Guinard. So in this contribution, they say that they find new open clusters. So what has made the difference? Because it was thought that it was complete, but now with Gaia DR2, what made the difference that allowed to find new open clusters at these distances?
Yes, well, it was thought to be complete, but it has been revealed that several already cataloged clusters were asterisms or were just not real clusters. So we are keep increasing the number of clusters in that range, and also because of the data mining algorithms, right? Because prior to this, we were looking for clusters, kind of looking for densities by eye, And now we are using these machine learning and data mining algorithms that are more clever than we are, right? So they can look for slight of densities, let's say, with not as high the contrast with the field.
Okay, and in this case, you think you are now complete, or there will be surprise in the?
No, well, actually, in the work by Friedrich Anders that was presented by Santi, we do some kind of completeness study, and we by age bin. So for the youngest clusters, we are kind of far from complete. We are like 60%, something like this, complete. And for older clusters, we are reaching 95, 98% of completeness. So we are not still yet complete, but yes.
That's good. Thanks.
Okay, good. Thank you. I have a question also. If there is no other question in the audience, I see there is another comment. I will go to it later. The question is to Arellano Córdoba regarding these radial abundance gradients that they found that in the Milky Way there is no flattening in the oxygen in the central parts of the galaxy, while in most of the previous works there was this flattening. I don't know if you, Arellano Córdoba, is around, and if she can comment something.
Sorry, with the -1A, yes, I hear. Yes. Okay, yes. Actually, we don't find this kind of flattening in the oxygen abundances within H2 regions. We also have new observation from GTC that we are now analyzing. I can say that we don't find that kind of flattening. We are preparing now the results. We're using that kind of observations that are in the inner part of the disk using optical from H2 regions. Mm-hmm.
Okay, and well, I don't know the details of this kind of gradients, but basically my question was more on which is the difference between your work and the previous works, and if it is the tracer, the thing that determines that in you using H2 regions, you are not seeing the flattening, but other people may be using other tracers, they are using this flattening, and maybe if this can have an impact on the idea of how the galaxy was formed, because it is different from H2 regions than from other tracers.
Yes, maybe you are referring to using a star, right? Using, yes, of course, but I'm not sure if the stars are looking for more in the inner disk of the galaxy. Maybe yes, I know, but in optical spectrum in H2 regions, for us, it's very difficult to have the kind of observation for the dust. So we had we need Brian H2 regions to have the observations. So the thing that is with Cesar Esteban and Jorge Eduardo, we are now observing this kind of regions, but for H2 regions in the optical, it's different. In any case, with observation of H2 regions with infrared lines, I think also is not the metallicity gradient is also not possible. But I'm not sure if this is the respond your questions.
Thank you. I see that there is another person in the audience that wants to.
Yeah, can I have some puntualization? Well, in fact, the people that found that flattening in the inner part of the galaxy were us. So we found in a paper 2 years ago that there was some kind of flattening in the inner part of the galaxy, but with new data, with the new Gaia parallaxes, we modified that, and now we have data in the highly extincted H2 regions at 3-4 kiloparsecs to the center of the galaxy, and we for sure we can discard that flattening.
Okay, great, thank you. This solved the question. Great, thanks.
So there was a question here by Jose Bosch. What software do you use for doing photometry of open cluster? And then Jose Caballero say IRAF or some customized Python code, but maybe someone wants to answer directly in the Zoom channel so everybody can benefit, and then we feel their presence instead of writing. It's okay? So it's already, anyone wants to comment there? Okay.
Hi.
Hola, Ricardo. Tell.
I think that the best software to do photometry in crowded fields like open or globular clusters is the DAFOT, but not the version implemented in IRA. It's the DAFOT 2 version, which is a floor-time code and everyone can install in their laptop or in the computer. But it's not very straightforward to use the first time. Because you need to compute the PCF of the image and all these things. So it's the best, but it's not straightforward to use.
Is there any manual for that, or?
There is all manuals, but I don't know if there is something updated.
Mm-hmm.
Okay, I think that if there is anyone else that wants to make a question or start a discussion, we are at almost a 4:15, so it's time to go to the SEA General Assembly. It's the first call, and the second call is it's at 16:30 minutes. So if nobody else wants to add anything else, just thank you a lot for coming, for being here, and hope to see you in person at some point in the close future in a new SEA.